This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Our next speaker is Kin Ian Lowe from University College London.
Right. Can you hear me? Yes. Thank you, Ben, and thank you for the organizer for this opportunity. So I'm Ian. I'm a PhD student at UCL, and I'm going to tell you about our recent work on an attempt to connect quantum contextuality to natural language. And this is joint work with Shane from Condela. So I'm going to first tell you about a quick introduction to contextuality in both the quantum world and natural language. And I'm going to introduce the what we call the generalized Winograd schema challenge. And we found that more expensive LLM turns out to be better at the generalized Winograd schema challenge. And there will be some cat pictures. So what is contextuality? So measurements in the Copenhagen interpretation is very weird. It's probabilistic. Some people didn't like it, so they wanted to fix it with what we call a non-contextual realistic hidden variable theory. And realistic simply means that the measurement outcome should be pre-existing and deterministic. And non-contextual simply means the pre-existing outcome should be independent of the context. And that is the sets of other measurements that should be measuring at the same time. And the probabilistic nature would be explained by our ignorance of the true state of the system. And unfortunately, that won't work. And because of the Bell-Coulson-Specker theorem, which says that no non-contextual realistic hidden variable theory would explain everything coming out from quantum mechanics. And proof is by example, which I'll give you one now. Bell's inequality is a proof of the Bell-Coulson-Specker theorem. And the idea is you have a shared system between Alice and Bob. So Alice here, Bob here. And they have got two observables each. And these two observables are incompatible, and same thing for these two. And the outcomes of the measurements of the observable will be either +1 or -1. And you can prove that the correlation as certain linear combination of the correlation satisfy these 8 inequalities. And the proof is quite straightforward. So you basically consider every possible realistic value assignment to the observables, and you can observe that the value of the correlation is either +1 or +2 or -2. So when you consider a probabilistic mixture of these hidden states, you get a value of this correlation between -2 and +2. And it turns out that the Bell state with these observable would violate one of the Bell's inequality. So quantum mechanics is contextual because of this. And there's some work on the computational power of contextuality. And in a Nature paper, Howard and the others show that contextuality is needed in magic state distillation, which is a key component in fault-tolerant quantum computing. And in another line of work, Anders, Brown, and Rosendorf show that contextuality can leave linear classical computers to universal ones. So the bottom line is there's some kind of magical computational power behind contextuality. And let's switch gear to contextuality in language. So the idea is very simple. Basically, almost every word in natural language is ambiguous. In this example, the word bank has 9 different meanings in the Oxford English Dictionary. So in the first example, he sat near the bank, reviewing his account details. Obviously, bank here refers to the institution where you put your money in. But if you change the context to observing the flowing water, then the meaning of bank becomes the bank of a river. So that's what we call contextuality in language. And I want to show you what we think is a perfect example of contextuality in language. And that is the Winogard schema challenge. It was proposed as a replacement for the Turing test. So let's look at one of these, one of his examples. So the cat doesn't fit into the suitcase because it is too small or big. So the question is, what is it? And the core idea of the Winogard schema is that there will be 2 versions of the same sentence. And if you choose so we call this a special word. And if we choose the special word to be small, then it refers to the suitcase. And if we choose it to be big, then it refers to the cat instead. So it really requires some kind of common sense knowledge of the physical world, of like smaller things would fit into a larger container, and so on and so forth. So it was really proposed as a test of machine intelligence. And a natural question to ask is the Winogard schema challenge contextual in the quantum sense? And the answer is no. So you can think of the special word as Alice, and it has a choice between 2 observables, but that's nothing more, so there's no Bob, so therefore no quantum-like contextuality. And just to give you a bit of context, so back in 2016, the best model achieved an accuracy that is slightly better than random chance. And around 2019, when LM came out, there's like a phase transition from almost random to almost 100% accuracy. So therefore, we propose the generalized Winogard schema. So in the original Winogard schema, we have only got 2 observables, so therefore it's not quantum-like contextual. What we did was basically introduce Bob into the picture, and in doing so, we have got 4 observables, and there are joint measurements between A-B pairs. So this is one example of a generalized Winogard schema. So X and Y belong to the same. So that's the first special word. That's Alice, cannibalistic or herbivorous species of animal. One of them was very hungry. They noticed each other when they were roaming in the field. After a while, one of them is no longer hungry. That's the second special word. That's the Bob. And the question is, what is one of them referring to, and what is one of them referring to? And yes. So to correctly answer this question, you need to understand that cannibalistic animal would potentially eat its own kind when they're hungry. And this example is designed to resemble the PR box, which is known to be the most contextual system. So we send the example to Amazon Mechanical Turk to collect 410 judgments. And we find that there is a positive violation to the balance inequality. So the example is contextual, although it's not like a PR box, which has a maximum violation to the balance inequality, but still is contextual. So human subjects were very expensive. We paid $1 per answer. So we were like, why didn't we use LLM to evaluate these examples? So that's what we did. And there's some very interesting correlation going on. So this table is sorted from the cheapest model to run to the most expensive. And the most expensive models gives you the highest violation to the balance inequality. So we tried to understand why the GPT 3.5 models, which are the cheapest model, why didn't they exhibit contextuality? And we find out that precisely because they didn't realize a cannibalistic animal would eat its own kind. Right. So, conclusion, both quantum and language exhibit some kind of contextuality in their own sense. And we propose generalized Mail-Guard schema challenge, which by design is contextual, and in fact quantum-like contextual. And it seems like better LLMs are better at generalized Mail-Guard schema challenge. And that leads to the prospect of using contextuality as a benchmark to evaluate LLM reasoning abilities. And for future work, if we want to use Gen Reno as a benchmark for LLM, we need a sufficiently large data set of examples. And on a very different line of work, we can connect contextuality to phenomena in psycholinguistics. For example, like there's research into eye movement when people were reading text. And for that line of work, please see Daphne Wang's line of work. So that's the QR code to the paper. That's my LinkedIn. Feel free to ask me any questions. And that's Ferry, not Alice. Thank you.
Thank you very much, Ian. Are there any questions? Yes, we've got a question up the back there.
Yeah, thanks for the talk. So we know that the framework, the mathematical framework of contextuality and even DiscoCat is much more rigorous than real natural language, because if you go to like Twitter or Reddit or 4chan, you can see that the real natural language doesn't always follow like true grammar. So unless you are, unless the Noam Chomsky's idea of universal grammar is actually true, but this idea has been challenged in recent large language model research. So do you think that it is more likely that this kind of contextuality and maybe more rigorous grammar actually exists in the human reasoning process, not actually in the natural language level? Thanks.
Right, so the question was whether or not contextuality exists in human reasoning processes. That's a good question. We didn't really explore that. But if you think of natural language as a proxy for human reasoning process, then I guess this work would be a gateway to a better understanding of whether or not contextuality exists in human reasoning processes.
So like by natural language as a proxy of human reasoning process, do you mean that something like the internal monologue process of like something like system to reasoning?
Can you repeat that, please?
So like by saying natural language as a proxy of human reasoning, do you mean something like chain of thoughts, or maybe the internal monologue of like human reasoning process happens in some people, but not always happen for all the people?
Yeah, unfortunately, I'm not expert in the question, so I guess we can like discuss about that like in the break.
Yeah, thanks.
Thank you.
All right. In order to keep to time, we're going to have one more quick question while Farad gets his slides ready. Fire away.
All right, yeah, thanks for the great talk. The way I understand it, you have this idea of generating data to evaluate the model, but basically you only evaluate the outcome. Are there approaches that look at like the internals of the model and to understand whether like this reasoning is really being performed, or so like interpretability avenues there?
Right. So there are a lot of works in the AI field, I mean, in the LLM fields, which looks into the internals of an LLM. But in our work, we didn't really look into that. But I'm happy to chat with that. Thank you.
All right. If we could thank Ian again, thank you.